Okay, so hello. Today we will talk a little bit about the Shadowgun. And we have Peter Smelek, a graphics programmer from Madfinger Games. He joined Madfinger Games specifically to work on a Shadowgun project. And I'm Rinaldas from Unity Technologies. And the short intro about the Madfinger Games, it's a small company in the Czech Republic, and previously they released a quite well-received Samurai and Samurai 2 Vengeance. And they started working on the Shadowgun project in February this year, and they started 4 of them, and now team grew up to 10 people. And actually Shadowgun was just released yesterday. And Shadowgun is a third-person shooter where you basically run, gun, and hide and shoot, and you are playing as a muscular guy, but in a good way. And it's a sci-fi setting, and if you look at the sci-fi movies, usually they have quite a lot of contrast, quite a lot of style, quite a lot of mood, and you can usually see a lot of blinking lights, a lot of emissive surfaces, a lot of panels which glare at you, and very dramatic lighting. So that's what guys wanted to achieve with the Shadowgun, and it has quite a lot to do with the shading and the lighting of the project, which we will talk a little bit later. And as well, you usually expect quite a lot of eye candy from the sci-fi, and there is quite a lot of cheap eye candies in the Shadowgun. As well, the world of the Shadowgun is pretty big. We wanted to have the real game, which is kind of big and with a lot of levels, and at the same time, to have it look kick-ass. So, it's a time for the trailer.
We strongly prefer you return Dr. Simon to us unharmed.
You're assuming this mission will be easy.
Yeah, no worries. Charge more for this job.
So as you see, there is quite a lot of it doesn't really look photorealistic. It looks more of a little bit cartoonish, and not cartoonish, but a little bit dramatic and very high contrast. They wanted to, the artists on the project wanted to emphasize that as a sci-fi mood. And the target hardware, there is a pretty big range of the target hardware for the Shadowgun. On the high end, we have an iPad 2, and we have support for the Tegra 2 and iPhone 4, iPad, iPhone 3GS as a lowest platform. And actually, there is a coming enhanced version for Tegra 3, which is developed together in a tight cooperation with the NVIDIA. And I would like to mention a little bit about the hardware challenges, because the hardware range is pretty wide. So it's an interesting thing to note that on the iPad 2, for instance, we are CPU bound. That is because the GPU is very fast on the iPad 2. And we're not taking the full advantage of the multi-cores yet. That is something coming up in Unity pretty soon. And on the other hardware, like Tegra 2, iPad, and iPhone 4, we are actually GPU bound. It's because the GPU is not that fast there comparatively, and there is quite a lot of pixels to fill. And again, on the iPhone 3GS, we are CPU bound. So it's a little bit interesting to balance between this, on some platform being GPU bound and being CPU bound on other platforms. So we had to figure out this balance. And to get it running well on the low and hardware, like iPhone 4, we had to optimize the GPU rendering quite a lot. And there's quite a lot of tricks and optimizations, which we'll cover later in this talk. And I just wanted to show you the difference between the iPad 2 and the iPhone 4, for instance. On the iPad 2 with the 4x multi-sample anti-aliasing, we are taking a little bit less than 10 milliseconds on GPU, so we could run 100 frames per second. And at the same time, on the iPhone 4, we are GPU bound, so we are taking 30 milliseconds to render. And on iPad 2, obviously, we have quite a lot of room in the future for improving the look of the Shadowgun, for instance. So, as I mentioned, there were quite a lot of optimizations on the GPU side, and all the shaders which you'll see in the game, all of them are hand optimized. And I just wanted to stress a little bit that the precision in the shaders are very important. That just by tweaking precision, you can get quite far. There is another thing which I wanted to mention is the order of the rendering, and it's not that important on the iPhone, but on the Tegra, you need to, because of the overdraw in the game, you need to help a little bit Tegra with to solve the overdraw. And we had to order stuff specifically for Tegra. And what we do is we pick the biggest occluders which are close to us, like in 10-meter distance, and we always render them first, and we always sort them so they are front to back. And all the rest of the objects which are behind, they are sorted just by shader. So those front ones occlude pretty well, and in this way we help GPU to find the best occluders and occlude stuff behind. And on iOS, we just sort by shader because it's not that important. The sorting by shader helps to reduce the API workload. And specifically in Shadowgun, we have improved how dynamic geometry is being submitted to GPU internally. So all those things will be coming in the next version of Unity. Another challenge with the Shadowgun was the memory. And as you can see, the iPad, iPhone, 3GS, and some Android phones, they're pretty low on the memory. So we basically have only 100 megs of memory. And the simplest solution we picked, as you can see in the script, potentially you can see it. We just pick some platforms, and on those platforms, we skip the highest MIP level. And that's basically it. And on the Tegra, we always use DXT5 compression. And it's very easy to do. You just, in the build window, you pick build for Tegra, and it will recompress all your textures to use DXT1 or DXT5.
So now I will talk a little bit about lighting and shading in Shadowgun. Lighting and shading is actually crucial for overall look of the game. And if you want realistic lighting, you usually pick up the global illumination solution. Global illumination is integrated into Unity engine. And for static geometry, it can be pre-computed into textures, which are then called light maps. But for dynamic geometry, you need to utilize different approach. So for dynamic geometry, we use new feature of Unity, which is so-called light probes. Light probes are actually points in the environment which capture information about incoming lighting. And then if you put a large amount of such samples into scene, you are able to reconstruct the lighting in any point of space by interpolation from neighbor light probes. Light probes are internally stored as spherical harmonics. And there is usually about few hundreds of light probes in scene, which are spaced about 3.5 meters. I can show you a screenshot when yes. Sorry. So on this screenshot, you see light maps on static surfaces. You can notice that they are quite low frequency information there. And for this reason, we use quite low resolution textures, but uncompressed, because compression in case of light maps can introduce very visible artifacts. But we prefer to have low frequency but perfectly smooth GI lighting. And according to light probes, using the spacing about 3.5 meters, you get perfect matching between dynamic objects and the static environment. So it's look really consistent, the lighting.
So it's a short movie which I don't know if you have seen.
We'd like to show you Shadowgun, made by Madfinger Games, that utilizes some of our in-development technology. First thing we'd like to show you is the new character shader driven by an artist-controlled, custom bidirectional reflectance distribution function. It's full per-pixel bump mapping and specular and runs really fast on mobiles. You can see the character is dynamically lit, additionally using light probes to react to lighting coming from the environment. We're introducing light probes into Unity. Light probes are the spheres that you can see in the air, which sample all incoming lighting at a given point in the scene. Unity builds a structure of tetrahedra out of these, which allows for super fast interpolation. Light probes capture direct and bounce light, and also from emissive surfaces, which means your characters get beautifully lit by their surroundings. The technique works by picking up nearby probes and interpolating them at a character's position. It's a very fast and efficient way to get real-time lighting on your character that matches the surrounding baked light maps. We can also add additional real-time lights to the character's probe almost for free. You can see the effect in this slow-motion zoomed-in video, where we correctly capture the muzzle flashes on the character. Now this is all happening on a mobile platform, as light probes are so efficient at aggregating multiple light sources affecting a given object. This Shadowgun footage is in-game and runs at 60 frames per second on the iPad 2. These new features are part of our big push to make Unity the best platform for delivering high-end content across the browser, desktop, console, and mobile. And we can't wait to see the awesome games that you make with them.
One second, I will try to enlarge the presentation slides because they look very small on the screen. Sorry for that. No. Maybe we could enlarge the screen a little bit? I don't know if that's possible. Anyway, another thing which is very important for the look of the game is the crispness of the texture and crispness of the overall look. So usually people use mip-map biasing to increase the resolution of the textures, so forcing the lower mip levels to be used. We found that it's much better to use anisotropic filtering instead, and it scales with the performance much better because you can actually limit the amount of the anisotropy for specific platforms. It doesn't give you, there is no aliasing. Usually when you increase the mip bias, then you get a lot of small aliasing, and that is not the case with the anisotropic filtering, and it's much more portable as well. And there is one more trick on the iPhone, on the iOS hardware. iOS hardware can actually, it can be very smart, and it can prefetch textures before it gets into the pixel shader. But if you are doing mip-map biasing inside your shader, inside the pixel shader, then the hardware is not able to prefetch. So you lose performance on that. So we're using anisotropic quite a lot.
We have discussed that we use GI for static lighting, which means that the lighting is pre-compute, and when you pre-compute the lighting, you can have the problem to reconstruct view-dependent part of the lighting, which is specular lighting. You can basically do it. For example, Half-Life 2 engine does it by pre-computing 3 light maps instead of 1. It pre-computes the light map from 3 cardinal directions, and then in runtime, in Pixel Shader, is able to reconstruct specular lighting or even use normal map for diffuse lighting. But for mobile GPUs, this approach is still prohibitively expensive, so we chose another approach how to add specular to light maps, which is basically cheap but looks good enough. And what we do is following. We attach point light to the camera position together with some offset, and then calculate per vertex specular from this light, using vertex colors to mask the glossiness of the materials. Using this approach, you basically get specular highlights on all surfaces facing the viewer, as you can see on the screenshot. For metallic surfaces, it gives you mostly correct look, but there are some issues with this approach on geometry, which is lowly tessellated. So their highlights on such geometry are not quite sharp. It is very dark, I don't see anything.
Unfortunately, it's very dark.
Yes. Now we will talk a little bit about volumetric effects. By volumetric effects, we usually mean phenomena that are coming from scattering in atmosphere or participating media. This is usually a class of effects like glows from lights, light shaft, fog, and stuff like this. Those effects are usually implemented by rendering additively blended surfaces, and you need quite a lot of such surfaces to create convincing effect. Then you video now? Yes. I actually think that we should show the video slightly later, but never mind. To optimize rendering of such geometry, you basically can do 2 things. First thing is obvious, and it means that you use as simple pixel shader as possible. You can even use pixel shader which doesn't sample texture at all, and you basically calculate the intensity of the function per vertex. You usually use some kind of gradient for such effects, so it's not problem even with low tessellated geometry. And if you have some more complex function, you can just add more vertices and still evaluate the function in the vertex shader. Second step to actually optimize rendering of such surfaces is to limit amount of pixels rendered by these surfaces. What we do in Shadowgun is actually control size of surface on the screen according to position to viewer. What we do that as surface approaches the viewer, it gets more and more transparent, and at certain point it starts to shrink. We basically define which edges are fixed of geometry and which are moving, and when surface is transparent enough, we start to shrinking until the point that the geometry is only line, and so it doesn't generate any pixels to rasterize, and you have almost free. It renders fast. So on this picture, you can see the blue thing actually represents the shaft of light, and the red edge is fixed one, and the yellow edge is the movable one. The green arrows are actually handmade normals at vertices. And as viewer approaches this light shaft, the yellow edge starts moving towards the red edge, and the number of pixels on screen is getting smaller. In the video, you have already seen, maybe you didn't notice it, but as the player moves toward the rotating shafts, they are shrinking. Now you can see the effect in action. And using this approach, you basically eliminate the bottleneck on surfaces which hurt the most, which are the ones intersecting the clipping plane. And also it looks slightly better because if you don't control the transparency according to distance to camera, then you have ugly intersections on the camera plane.
So the character is a very important part of the game, of course. And I will brief a little bit on the character. It's using the diffuse texture, which is 1000 by 1000, and the normal map texture is 512 by 512. It's actually uncompressed. That's the reason why it's a smaller resolution. And we found that uncompressed texture in this case is much better than the PVRT compressed. And some of the textures are actually 16-bit compressed. On the characters, we're using special lighting lookup textures, and those textures usually are 128 by 128, and they are not compressed. Most of the characters in Shadowgun are below or around 2,000 vertices and around 25 bones. So the next, almost invisible, the character lighting. I hope you will be able to look at those slides online afterwards, and it will be much cleaner. But character lighting, so the way how the character lighting was developed for the Shadowgun, initially it started to me looking for a way to optimize per pixel specular, because usually per pixel specular is using power operation, and on many mobile GPUs it's pretty expensive operation. So instead we developed a way to just use a special lookup texture. And you can see below there is a small shader, lighting shader in Unity, which that's exactly the shader which is used in Shadowgun to calculate lighting, per pixel lighting on the character. And it starts like a usual shader, like a usual function, usual blindfong function, which calculates dot product between normal of the surface, per pixel normal of the surface and the light, and then dot product between the normal and the half vector. But then instead of doing all the math operation, it just does a single texture lookup. And that texture lookup gives a result. In the RGB channels, we encode a resulting diffuse of the light, diffuse value of the light. And in a specular, we encode in the alpha channel, we encode specular. And then there is a very simple operation which combines them together, both diffuse and specular. And as you can see, because there is no color in specular, so we're actually using a specular color. It's a diffuse texture. It's not coming from the light, but it's coming from the diffuse texture, and it gets kind of interesting effect. There is the good side of this approach. It's very flexible, because in that texture lookup, we can encode quite a lot of information, and we can do quite a lot of offline calculations. For instance, we put a so-called tri-light, where you can encode both key back and the fill light. And on the right side, you can see there is a small shader extension which we wrote to generate that texture. So basically, artists can tweak those parameters, and they exactly see how this texture will look like, and they can see the result on the character usually at the same time, because the shader picks up that texture and immediately you see the changes. So on top of the tri-light, we can do a wrap lights, so that they are very important for the skin where there is some sort of subsurface scattering inside the skin. So it doesn't give the plastic look. And we can even encode strange lobes for metallic surfaces, and we can do an energy conservation in the specular highlights. So all of those comes basically for free. It's just an offline calculation of that texture. And the good thing, soon it will be on the asset store, both the editor extension and the shader. So you can use it in any game. And the next step is how we combine the lighting. So it was already covered. So basically, we just calculate per vertex. We calculate light probe, lighting coming from the global illumination, coming from the walls, basically. And we combine that into this. Per object, we calculate a spherical harmonic. And then we evaluate that spherical harmonic per vertex. The good thing is that we can easily add more lights into that spherical harmonic, like a muzzle flash comes for free because we just add it into the spherical harmonic. And then we have to combine per pixel lighting and per vertex lighting from the global, basically global illumination and the illumination from the, together with the illumination from some sun. And we do that by simply modulating, multiplying per vertex and per pixel lighting. That is completely not physically correct, but it gave a very nice look which artists were after. So it gave this sci-fi, over-the-top kind of lighting. Should I show them? Later. Okay.
Now I will talk a little bit about shadows, how we did it for Shadowgun. Usually, for mobile devices, you can use what is called so-called blob shadow. It is actually darkening texture with circle shape, which is projected under the character, and it doesn't react to changing postures of the character, so it's completely static. It's not so bad, it is better than nothing, because then you have some sense of depth of characters in scene, so you don't think that they are floating in the air. But with slight modifications, you can do quite better approximation for shadows. And what we did is following. We basically approximated the character by 3 spheres. One sphere is located at the left foot position, another in right foot position, and one in the pelvis position. And then we, in vertex shader, calculate ambient occlusion between those spheres and the plane below the character. The expression of ambient occlusion between sphere and plane has quite complicated derivation, which was first presented, I believe, by Inigo Giles from RGBA demo group. You can look up his article on internet. But the result of this derivation is very simple to be used. So you basically calculate 3 ambient occlusions from those spheres, combine it with minimum blending function, and then apply it as darkening to the tessellated plane below the character. On this screenshot, you can see the tessellation of the shadow receiving plane. You can notice that the tessellation is higher to the center where you get the high frequency shadows. And on second screenshot, there is visible composition of this shadow darkening with the scene. And we also have seen the video in motion of the shadows. And now I will talk a little bit about screen deformation effects we did for Explosion. We can start with some videos. So the screen deformation basically creates illusion of sonic blast effect. It is popular in modern games, and it is usually implemented by post-process. By post-process, standard post-process, I mean that the calculations are performed in pixel shader. For mobile devices, for current generation of mobile devices, you cannot afford to have even very simple post-processing shader. So what we did is move those calculations to vertex shader instead. And how we did it? Basically on screen you see classic post-processing effect which renders one quad. It means two triangles and performs all calculations in pixel shader and outputs it on screen. But instead of using this quad, we tessellated screen space little bit more. We use, if I remember correctly, 30 vertices horizontally and 25 vertically. We create such grid. And then in vertex shader, we calculate distorted UV coordinates and pass it to pixel shader. And pixel shader only performs fetching of source texture with those distorted UVs and outputs it on the screen. So basically it means that you don't perform any additional work as if you don't have the post-process because you always have some kind of final bleed to the screen. What we also did to emphasize the blast effect is add some kind of colorization together with the distortion of screen as you seen on the video. And it is based on projecting center of explosion to screen space and then creating some kind of glow in that position, but with much higher intensity and much shorter duration. And last topic I will talk about is about dynamic fluid surfaces. We can again start with video. Just notice how the water reacts to moving characters and shooting. So this technology was created especially for Tegra 3 version, and you probably know this effect. It is very old school kind of effect. You basically simulate this surface in 2.5 dimension. It means that it is height field. And what is necessary to perform such a simulation? You basically keep two-dimensional arrays. One hold current height in a certain vertex and another hold the velocity. Then each frame you update the positions, velocities and reconstruct mesh from such height field. You only need positions and normals for such mesh. You don't usually need UV coordinates for water, or if you need them, you can generate them by simple planar projection. And on this slide, I will not go to the details about those formulas, but though if you are interested, they can be found in presentation from 2008 by NVIDIA on GDC, and a link to this presentation is in references section. But as you see on picture, the updating of velocities and position basically means that you need to access the neighborhood of the red pixel, which is pixel being processed. And this accessing of the neighborhood hides in itself optimization for opportunity for optimization. And what I mean is following. If you access neighborhood of pixel, then you have to somehow handle, in special case, pixels on the borders to avoid out-of-bounds access to the arrays. You can do this straightforwardly by clamping the indices, but if you use this approach, then you add a lot of branches to the code, and a lot of branches in the code mean potentially slow performance. So it is slightly better to add one pixel wide border around the simulated area, and this acts as a safeguard, and you don't need to care about out-of-bound access anymore. Now about the performance numbers. For grid of 128 vertices, straight C++ implementation on Tegra 3 takes about 0.9 milliseconds to execute, and using naive conversion to assembly code, which utilizes the vectorized neon instruction, we cut this time almost to 1/2, which means 0.5 milliseconds for quite a large water surface. Now we have the mesh of the water ready, and now we need somehow to display it, so we need shading of the water surface. Shading of water surface is usually very complex, and it is not possible to do same approach as you use on desktop machines on consoles. You need something radically more simple. So what we did is use just static reflection, which is captured in CubeMap, in pre-rendered CubeMap. The CubeMap is generated in editor from certain position in space. And then we actually, according to Fresnel term, we blend between the reflection and color of the water. Color is calculated by very ad hoc solution which combines color for shallow water and deep water. So you have slightly more complex color variation, and you combine this with the reflection, and it looks quite reasonable. So if I believe this was the last slide.
So the only thing to add here is that currently the water shading is mostly limited by the GPU performance, and it would be much nicer to have a more complicated water shader, but that will come in the future with the better GPUs. And that's all slides we have. Thank you. So if you have questions, please do. If you don't have questions, you can play the game.
I'm sorry, but I cannot hear you.
Could you speak up a little bit?
So when you moved your distortion from being a full screen quad to being split into more anticipated grid, can you talk about how you actually set that up in Unity?
This is not integrated in Unity. It is custom script and shader we wrote specifically for Shadowgun, but I don't see why it cannot be released
So basically, you just create that geometry inside your script, and you animate it
Yes.
inside the script, and then you just put the rendered target on top of that grid. So it's not like you can do it yourself. It's not something from Unity, basically.
It is actually very simple. So
It's probably something we could put on the asset store as well in the future. Maybe.
Do you guys have any like general advice for mobile shaders or how to achieve sort of standard, are there things to avoid, any pitfalls that on a normal desktop GPU you won't have trouble with, but
Well, the main thing is precision. Usually, the question was how to improve performance coming from from desktop shaders to mobile shaders, and usually you don't care about the precision that much on the desktops. Sorry, and on the mobiles, it's very important that you specify the lowest possible precision, like fixed or half, depending what you're doing. But mostly for colors, you are using fixed. And for normal, sometimes you can use fixed, sometimes you can use halves. And in the vertex shader, usually still you use full precision. It's not a problem. But in the pixel shader, it's very important to compact. Then there's stuff like alpha testing is really bad on mobile GPU, so you try to avoid that. I think there is no alpha tested surfaces in Shadowgun at all, or everything is alpha blended. But we have another presentation in 1 hour, which will cover the shaders, the mobile GPU optimizations, basically, if you want to have more in-depth. It's in CA room, so they will be more in-depth. But precision is the most important, usually, when you're coming from.
Can you clarify the performance in the iPad 2
Well,
and also for the iPhone?
so on the iPad 2, on the GPU side, it runs on around 100 frames per second. It takes like 10 milliseconds. But since it's bound by CPU, it can't. Like if we would have only rendering, nothing else, then it would run 100 frames per second. Since we have much more stuff going in the game, it usually runs. The final build, it doesn't run 60 frames per second because there's a lot of stuff added, and we are optimizing that. So in the future, so right now it runs around 45, 50 frames on the iPad 2. So, but I think there will be updates which will get it running to 60, and it was running 60 before. So on the iPhone 4, it runs 30 frames per second most often. But there are always situations when it can drop below that.
When we're finally going to modify the game engine to take advantage of dual cooling, any prediction on improvement?
Sorry, could you please repeat?
When you mentioned that this is based on a single CPU because it's not optimized for
It's
CPU, so when you do optimize it, do you have any prediction in terms of the increase in performance?
yeah, so we're using the two CPUs. It's just that we are not using them 100%. I would say we use around 20, maybe 30%, depending on the situation. Because right now we do skinning, particles, something else, some physics on the two cores. But in general, I would expect, for example, when we tried with the skinning on Tegra 3, it would, if you're using, it is 4 times. When you are using 4 cores for skinning, skinning performance gets 4 times, 4x basically. In some other cases, it will not give you this huge performance improvement. But since we are having now the rendering part is running in parallel with the scripts, it's not in the build yet, not in the current Shadowgun build. It's coming a little bit later. So I think we will get around 40% performance improvement, 40, 50% by using 2 cores. Long answer. Any other questions? Yeah, this one first. So the question is how many draw calls and how many vertices on average. So on average, it's actually pretty low on the vertices. The guys did a very good job on the art department. So it's around 30,000 vertices per frame. And on the draw calls, it's around starting from 55 up to 70, depending on the scene. And usually we have around 200, 300 objects, but they are batched to those 40, say, 70 draw calls. If you want to know the specific numbers on the iPad 2, those draw calls will take around 4 milliseconds, which is 1/10 of the frame, something like that.
Did you try running it just as an experiment on an Android phone, running like the latest Snapdragon processor, CPU with Qualcomm's latest GPU?
In general, we're running on an Android, but the question is specifically on, have we profiled? No, we haven't really profiled on the Qualcomm. Really. We tried it, like more or less looked at the performance, but I will not be able to tell you any specific numbers. But we can try. I mean, I don't know at the moment on the Qualcomm, but we tried pretty well. You had a question.
Yeah, so you had a slide that was discussing the per vertex lookup against the light probes, and then there was a subsection where you talked about pixel shading against the light probes.
No.
Where were you going here?
No, it's there is no, the light probes there per vertex.
Okay.
There is no per pixel lighting in
The second
case of,
part was a little confusing because you were talking about merging. And
yes, it's,
doing it per vertex.
yeah, exactly. We do per vertex light probes, we pass the result in the interpolator, and then we combine them in a per pixel with the per pixel lighting. I mean, it's just not feasible for performance on the mobile to do per pixel light probes, but you could do that on the desktop without problems.
It seems like your original primary target was for the iOS. What was your greatest challenge in retargeting the Android?
I wouldn't say it's iOS. I mean, we probably figured out quite early that the Tegra 2 will be a limiting on the GPU side because of the very big screen there, usually on the tablets. So quite a lot of time was, not a lot of time, some time was spent to optimize specifically for Tegra. So it was, we haven't really done any specific iPad 2 kind of optimizations, except we were more concerned about the iPhone 4 and Tegra 2. And on iPad 2, it just runs very fast. I mean, we did some optimizations which benefited iPad 2, and I spent quite a lot of time profiling specifically on the iPad 2, but it just because of it was easier. But our low-end kind of, the platforms we were optimizing, it was Tegra 2 and iPhone 4 from the start, I would say. I just, both. Yeah.
You mentioned you were using the spherical harmonics for the light bulbs.
Yes.
What frequencies are we able to use? Is it just for the diffuse component, or do we get higher frequency lighting effects?
So it's a third order spherical harmonic. It's a third order. So it's 9 floats basically, and it's only for diffuse lighting. You can't really encode anything more than that. In case of the Shadowgun, we have around 500 light probes per in scene, so it's not really a big issue of the memory. You could up the. There is no possibility right now to do it easily, but theoretically, we could up the resolution of the spherical harmonics in the future if it's needed. We have 5 minutes. Yeah. Ah.
I'm kind of curious, did you run into the issue of like the 50 megabyte limit on the Android market, and how did you overcome that?
We had run into it already, but it's not yet exactly solved. But the idea is usually it's to have a loader, like you from the Android store, you download a small application, which then downloads the rest of the game.
Were you using like asset bundles to do that, or did you just set up the textures?
We actually yet to do that. I mean, we did that for other games, but not for the Shadowgun specifically. But it's quite easy to just download the asset bundles. But it's yet to be solved specifically for Shadowgun. It's just other games are using this already. Yeah. One more question? Yes?
Can I expect that the C platform post-processing pipeline to benefit from this one-pixel border optimization you mentioned?
Sorry, the question if the post-processing would benefit from that. No, not really, because it's a specific for Fluid, I would say. It's we don't have any clamp. Like usually when you on the GPU, when you sample the texture, there's automatically there are clamps. If you say the clamp on the texture, then when you sample it, it will clamp it to the borders. That is inside the GPU. You don't need to. It doesn't cost you anything. No, it's a matter of on the CPU because we calculate because the fluid surface is calculated on the CPU. There, it's more important to do that. I think we're done. If you have some questions, you can just grab us and talk.
Thank you.
Thank you.